today's speaker. He completed his BSc from Presidency University. Then he did his MSc from IIT Kharagpur. Presently, he is doing his PhD from IACS Kolkata. Today, he is speaking about the thermal dark matter. Requesting everyone, please mute your microphone and turn off your video. If you have any question, then please write it in the chat box or raise your hand. I will take those questions after finishing the talk. Thank you. Over to the Dibda.
So thank you for inviting me in this Alumni Lecture Series. Hope you all are pretty much well. What should I do? Share screen. Sorry, hello?
No.
So host, it is saying that host disabled participant screen sharing. So
no, it was just enabled.
Oh, acha. Okay. So let's try again. Okay. So can you see my slides?
Yes.
And the pointer?
Yes.
Okay. So today I'm going to talk about dark matter microphysics. So mainly on the topic of thermal dark matter. So the existence of dark matter is well-established fact from various cosmological and astrophysical probes. So I'm not getting into those details, but as a particle physicist, we need to keep certain things in mind whenever we build some models of dark matter or predict some dark matter scenarios. So let me start with that. So the dark matter is non-baryonic component of our universe, and it's input from Big Bang nucleosynthesis. So from Big Bang nucleosynthesis, we know the baryon content of the universe, and those baryons cannot make the total mass which lies in the galaxy and galaxy clusters. So there must be some non-baryonic part. And this non-baryonic part has to be non-relativistic at the epoch of structure formation. So otherwise, if it is relativistic, then it would have the radiation pressure, and radiation pressure would negate the gravitational pull, which actually facilitates the matters to come closer and make structures. And it has to be stable. Otherwise, we won't see it today. And the name dark matter comes from the fact that it is non-luminous, so it has no electromagnetic charge. So these are the four features, and we have to keep in mind one number. So that is the relic density. So here in this picture, you also can see that this rho x is the energy density of dark matter in today's universe, and that is scaled by this critical density of the universe. So this is 0.25. So whenever, as a particle physicist, we build any model or check any dark matter scenarios, we have to keep these things in mind at least. So now, if you ask, so talking about dark matter microphysics, can you tell about the mass of the dark matter? And the answer is yes and no, because given these 5 things, we have a huge mass range, allowed mass scale for dark matter. So let me tell you at least the 2 extremes of this scale. So here, this is in natural units. So 10 to the power minus 22 electron volt mass. This is the lower limit of dark matter mass. So this number comes from the fact that, let's say dark matter is a boson, and it has to be confined into a typical galaxy. Then its de Broglie wavelength should match the length scale of the galaxy. So from there, you can estimate the number to be as low as 10 to the power minus 22 electron volt. And the upper limit comes from the stability of stellar clusters. So if a dark matter cloud hovers around the stellar clusters, it might disturb the stability of stellar cluster. So from there, we get upper limit of dark matter mass, which is of the order of, if I convert into electron volt, then it would be something like 10 to the power 70 electron volt. So lower limit is 10 to the power minus 22, and the upper limit is something around 10 to the power 70 electron volt. So this is a huge gap. And in between, there are a lot more mass scales there, and all these mass scales depend on either a particle physics models or a particular cosmological scenario. And in fact, dark matter can be of like elementary particles. It can be of some macroscopic object like primordial black holes. So in today's talk, I would confine myself to the particle dark matter. That means dark matter as elementary particle. So with this assumption, this complete mess, I would say, would not be resolved. So the point is how to break this degeneracy of this huge range of allowed mass scale. So there are two broad ways to deal with this. So one coming from beyond standard model. So the physics of ordinary matter, or so-called physics of 4%, is governed from the standard model of particle physics. But this standard model of particle physics has its certain deficiencies. And to mitigate those deficiencies, there are plethora of models, basically the extension of standard model, which we call beyond standard models. And in those models, there are a lot newer particles which are not yet been discovered, but there are proposals. So in those plethora of particles, we can find a suitable dark matter candidate. And then we wait for experiments to confirm that or to rule out that proposal. So this is one way. Another second way is building templates. So that means if we figure out the dark matter production mechanism, from these mechanisms, we can estimate certain mass or possible interactions of dark matter. So now if one can list out all the probable production mechanism based on some general principles and look for their cosmological implication, that would be nice. So it is something like in chemistry, what we have done, that depending on atomic number, we have periodic table, and we know there were certain gaps in that periodic table, but there were predictions about those missing elements based on the general principle. And finally, we discovered those particles, and discovered those elements, and those elements correctly fitted into those gaps. So similarly, we want to make a template or something like a table in which there will be probable production mechanism, and wait for future experiments or future observations to confirm which production mechanism is applied for those things. So once we identify the production mechanism, then only we go for specific models. So in this talk, I will be taking this second approach, simply because from experience we know physics of 4% matter is pretty much complicated. As you can see in this picture, that there are 20 odd particles, and the interaction are pretty complex. There are 3 kinds of forces. So it's far more complicated. Now we are dealing with physics of 25% matter. So it's a high probability that it would be more complicated than this physics of 4%. So we take the second approach. So only question remains that then what is the general principle based on which I can build my templates or classify things. So as we know that standard cosmology is based on hot Big Bang theory. So that means our universe is a thermal bath. So it's a thermodynamic system. So now we can ask ourselves that the question that particle dark matter was in thermal equilibrium or not at some epoch. So if this is the question, then we can list or classify particle dark matter into two categories. One is thermal particle dark matter, another is non-thermal particle dark matter. So for thermal dark matter, the dark matter number density is determined by the temperature and the chemical potential. So given the temperature and chemical potential, you know the dark matter number density at a particular. So you need not bother about any initial conditions coming from inflation. But for non-thermal processes, you need those initial conditions, because we know for thermal case, a thermodynamic system do not bother about its memory. So that's the good thing about doing thermal physics. Now, the question of chemical potential would further categorize thermal dark matter into two subcategories. One is having a zero chemical potential or non-zero chemical potential. Is equal to the anti-dark matter number density. Am I audible? Hello?
Yes.
Okay, okay, thank you. So
audio is basic.
focusing on this thermal part only, I will give a couple of examples of symmetric and asymmetric dark matter, and then I'll be done.
Deep, can I just interrupt? Actually, we could not hear everything in this slide, so audio was not available. Can you repeat the slide kindly?
Yeah, sure.
Please.
Okay. So from thermodynamics point of view, the question is that particle dark matter was in equilibrium or not, in thermal equilibrium or not at some epoch, at some early epoch. So based on that question, we can divide into two groups. The one is thermal, another is non-thermal. Now, for thermal dark matter, the number density is determined by the temperature and the chemical potential, because we know the equilibrium distribution. If it is non-relativistic, there's a Maxwell-Boltzmann distribution. So given the temperature and chemical potential, we know the number density. So we need not bother about initial conditions coming from inflation. So that means independent of inflationary scenario, we can safely determine the number density of dark matter at a particular epoch. So that's the beauty of thermal dark matter. But for non-thermal, it depends on initial conditions. Now, depending on chemical potential, we again can divide thermal dark matter into two groups. One is symmetric, another is asymmetric. So chemical potential 0 means that the dark matter number density is equal to the anti-dark matter number density. So these things are equal. But for asymmetric, when mu not equal to 0, then the dark matter number density is not equal to the anti-dark matter number density. So these things are not very exotic, because these things are also applied to the baryonic sector, because we know that in our universe, our universe is baryon asymmetric universe, only protons, not antiprotons. So these things can happen also to the dark matter sector. So we don't know, but still this is a valid proposition. Okay, so now the second comment I want to make here, that there is a time when dark matter not in thermal equilibrium. That means we know that a thermodynamic system takes some time to go to the thermal equilibrium. So we call that time lag is relaxation time, something like that. So intrinsically, there is always a non-thermal phase. But whenever we are talking about the thermal dark matter, here we meant that that non-thermal phase is not significant for determining the final abundance of dark matter. So there are scenarios where dark matter never ever reaches to the equilibrium, but also satisfy relic density eventually through some processes. But today we are not considering such kind of scenarios. Today we are focusing on thermal phase, and the thermal phase is important for determining the final abundance. So the next question is, what kind of processes can keep dark matter in thermal equilibrium? So there are two kinds of processes. One is elastic process, another is inelastic process. In elastic process, dark matter number does not change, only momentum redistribution happens. And in inelastic process, dark matter number do change. Now, for setting up the today's abundance, inelastic processes are necessary, because here we are considering the radiation dominated epoch where dark matter was relativistic. Then the number density is pretty much pretty higher what we see today. So we need some dark matter number changing processes to get the correct relic. So there comes this inelastic processes. But if the forward reaction rate and the backward reaction rate of these inelastic processes are equal, then there won't be any net dark matter number change. So we need these processes to go out of equilibrium, and eventually it should stop. So this out of equilibrium condition is reached due to the expansion of the universe. So what happens whenever expansion rate of the universe is higher than the interaction rate, then this process stop. So now the question is, then what kind of inelastic processes we can think of? So again, that is dictated from thermodynamic itself. So the question is that how dark matter thermalizes. So dark matter can be thermalized with two ways. So it can thermalize with the cosmic plasma, in which there is a photon bath or standard model sector, you can say. So thermalize with the photon bath, sharing a common temperature. And second kind of things it can happen, it can thermalize within itself. So now for the first case, we need dark matter standard model interaction. Otherwise, it cannot equilibrate with the standard model particles or photons, let's say photons. So then if there is the dark matter standard model interactions, then number changing processes should involve dark matter and standard model particles. And for the second case, there must be dark matter self interaction. And then the number changing processes should involve only the dark matter particles. So let's take an example, take examples. So this signifies the first case where you see that only dark matter standard interactions is there, and this is the simplest kind of topology we can think of in which dark matter number changes. So decay would not do, because we have said earlier that dark matter should be stable. So we cannot have 1 to 2 process. So only 2 to process is allowed. This is the simplest topology we can think of. And this is the simplest topology in the dark matter itself, where 3 to 2 process. This is a 3 to 2 process. 3 dark matter going to 2 dark matter. So that means the change of dark matter number is 1. So here the change of dark matter number is 2. So now when in a given Hubble time, one dark matter cannot find another dark matter due to expansion, then this processes stop. So that condition is given by this. So this is the interaction rate and this is the expansion rate. This is basically Hubble, depends on the cosmology. So so when these processes eventually stop, then the total dark matter number becomes constant, but the number density of dark matter dilutes due to the expansion of the universe. So when it stops, then nothing is happening, but universe is expanding. So that's when number density is diluting. And we know that dilution factor, and we can calculate from this equation, that is gamma T equal to HT, the freeze out temperature, and eventually we would know about the dark matter number density at that epoch, and then we can multiply with the dilution factor, and we would get the today's number density of dark matter, and that would satisfy the relic density. So only catch here is how to calculate, this sigma v. So this is the interaction rate. Sigma v is the collision probability. So this is called cross section collision probability, and it is multiplied by n chi. This is actually number of collision per dark matter particle. So I have written this collision rate for this 2-2 process. If I have written this for 3-2, then it should be n chi square sigma v 3-2. So this expression applies for 2-2 process. So now the question is how to determine this cross section. Can we do it without assuming any particle physics model? And the answer is yes, we can, and because of quantum mechanics. So you see that here initial state is dark matter, and final state is standard model. And this transition happens, and that transition probability can be calculated from scattering matrix, and that scattering matrix is unitary. So this is the implication of unitarity, that we can calculate maximum possible cross section. So this calculation is a bit involved. I'm not going into that, but please take my word that we can, from asymmetric unitarity, we can know about the maximum possible cross section. So in this paper from Grice Kamionski in 1990s, they have calculated the sigma v 2-2 process like this. So you can take this as the geometric cross section. So this is in natural units. So this is basically L square. That means centimeter square, something like that. And in this recent paper from our group, we have also calculated this for the 3-2 process and for N2 processes. This is something like this. So so given this cross section, we can estimate this relic density, and from there we have an estimate of upper limit of dark matter mass given a particular topology. That means the mass limit would change if it is 2-2 process, if it is 3-2 process, or if it is something 4-2, something like that. So dark matter mass depends on the what type of interaction you are taking. That means what type of topology you are applying into a theory. So for 2-2 process, I have shown that it is something around 100 TeV. And for 3-2, it is 1 GeV. And for 4-2, it is 1 MeV, and 5-2, 100 keV. Now, you would be wondering that, sorry, so as I go up to higher topologies, that means from 2 to 3, from 2 to I go to 3 2 and then 4 2 and 5 2, the mass has been decreased. So why this is happening? So, so now let me show you again this picture. So the collision probability of 2-2 process uh, is larger than the 3-2 process, because here the collision happens when dark matter finds another dark matter, but here dark matter, one dark matter has to find two other dark matter. So the collision probability is less. So when freeze out happens, the dark matter number density is greater for this 3-2 process. And now to get the correct relic, we have to reduce the mass of dark matter. So that's why uh, we see that for 5 to 2, it's around 100 keV. So now the question is that how long we can go. Can it be 7 to 2? Can it be 8 to 2? But there is a constraint coming from structure formation that the lower limit of thermal dark matter mass should be around 5 keV. So if I go to 6 to 2 process, then it would be reduced to something like 10 EV. So that is not possible. So we would stop at 5 to 2. So you see that from without doing any specific model, we can figure out something significant. But here's the warning. So this result would modified if I include another species of dark matter, if I include chemical potential. So here, whatever I have discussed till now is for symmetric dark matter, where there is no difference between dark matter number density and anti-dark matter number density. Now I would show that how, at least for 2-2, that this mass can change in the presence of chemical potential. So that means I'm now up to mechanism of producing asymmetric dark matter. So we start with a symmetric condition. So this is the symmetric condition when dark matter number density and anti-dark matter number density is equal at some epoch. So now to create a difference, we need two things. We now need two things. One is number changing process to satisfy the Rayleigh. The dark matter number should decrease. And as well as we have to create a difference between dark matter and anti-dark matter. So you can call it darkogenesis. This is just a reminiscent of baryogenesis we have done for standard model particles. So then what kind of topology can do the trick for me? So again, in this paper, we have found out this topology, and you see that here, if this process goes in this direction, chi to chi dagger phi, then the dark matter number changes by 1 unit. So here 2, here is 1. But if I calculate this n chi minus n chi dagger, that means here in initial state, there is n chi minus n chi dagger number is 2, because 2 chi particle and 0 n chi particle. So this is 2. And in final state, there is 1 chi dagger particle. That means n chi minus n chi dagger is minus 1. So the net change is minus 3. So then these two conditions are satisfied by this topology. So now having this topology is not enough. Now there is a certain microphysics involved to create a net asymmetry between chi and chi dagger particle. And what is that? So that is microscopic irreversibility. We need microscopic irreversibility. So that is called the CP violation in the interaction. So we need CP violation. So what is that? So this is nothing but this is the amplitude. That means the probability of going to chi to chi dagger. This is a forward direction reaction amplitude, and the backward amplitude should differ. If these two differ, then we would get a non-zero CP violation. That means this epsilon parameter is non-zero. So that is signified by CP violation. So now the dark matter relic density is a function of dark matter mass, the cross section, and this CP violating parameter that may be called asymmetric parameter. And now again, if we do the same calculation which we have done for symmetric dark matter, we would get this result. So when it is symmetric, then again we would get the dark matter mass around 100 TeV for 100 TeV. So here we have found 80 TeV for the semi-annihilation process. Whenever there is maximal CP violation that is given by epsilon goes to 1, then the mass bound is reduced from TeV to GeV. So it's a huge difference. So whenever there is a chemical potential, the freeze out number density of dark matter is higher. So we need lower mass. For I like to contrast two things, that here we are considering again the 2-2 process, but now the mass bound has reduced to 15 GeV. So that's all I have want to share with you, just to summarize what I have talked. That our approach is that from thermodynamic consideration and some interaction point of view, what kind of interaction we can thought of, that topology, N2, 2-2 process or 3-2 process or 4-2 process. And given a particular cosmological scenario, we can predict dark matter microphysics and then wait for observation to check these things. Whenever we are convinced about the dark matter production mechanism or about this microphysics, then only we, with positive data, go to the specific dark matter models. So that's my work. So thank you for your attention.
Thank you. If anyone has any question, please raise your hand or write it in the chat box. I have no question even in the chat box. So ma'am has a question. Please go ahead.
So Deep, I had a couple of questions. I'm going to just ask you the first one. So interesting work. So what you showed us is that you don't have any specific model of dark matter, and that's the good thing about your work, that it is model independent. And you just assume that, okay, if I think of this kind of interactions between DM and standard model particle, standard model and DM interaction, let's say this is, I'm not talking about what the interaction is, but if something like this happens, and then like a 2-2 process or 3-2 process, then how do you put the you put a bound on the mass maximum? Is that that's the maximum mass of dark matter that can happen, right?
Yes. That is the trick of asymmetric unitarity. So in asymmetric unitarity, we know about the optical theorem. So given the elastic cross section, we can put a bound on inelastic part. Okay. So from now, there, sorry.
Yeah, please go ahead. Please go ahead.
Yes. From there, we estimate this part. So this is involved calculation about partial wave analysis. So if you do partial wave analysis, then you get these limits, that how large can be your inelastic cross section. It depends on it depends on spin and the angular momentum. So
okay. Great. So those details are there, but can you go to a last slide? My question is that when you have this chart that you show, yes, this is very nice. Now you are saying observations. These are like direct dark matter detection observations. Are you talking about that? Because so what kind of, so my question is precisely this, that what kind of observations do you have in mind which can actually test for your model and tell us that, well, indeed, there is a, whatever that interaction is, but there has been record of 2 dark matter standard model interaction or 3 dark matter standard model interaction. So what are the experiments? What kind of experimental thing are you looking for? Yeah, that's the question.
I would give two answers. One for 2 to 2, 3 to 2. We have indirect detection experiments. So as you can see, the mass ranges are quite different. Then in indirect detection, if there is some gamma rays producing, so then its energy would be quite different as if it comes for 2 to 2. So the energy spectrum would be different.
Okay, so can one calculate such energy spectrum from your method?
Yes.
Okay.
So the point is now that this WIM dark matter and SIM dark matter, there are lot of many things that one cannot decide. So you know that WIM dark matter is heavily constrained now.
Yes.
So those things are there. So and I will give a second answer to your question, that for this asymmetric dark matter, if you can calculate the eta parameter, that means the difference between dark matter and anti-dark matter number densities.
Yes.
So we have calculated that for baryon sector, and that is pretty much robust from CMB observations. So if someday, I don't know which observation, so if someday we can calculate some n of eta of chi, like the eta of B, so then we would be sure that there is CP violation in the theory. So then we can think of this kind of scenarios. What would be this? So only point I want to make, that here we can solving the Boltzmann equation. So we have thrown some values, epsilon values or sigma v values, but whenever you do some specific DA models, you are just very much concerned about what are those values, or what is the sigma v or what the epsilon. So we are not bothering with the specific values, because we are not serious about it, because it may be ruled out later on. So we are just proposing some scenarios that it may happen. If someday one can confirm there is actually CP violation in the dark matter sector, then we would say yes, then you look for this process.
Yes. Okay. Thank you. So I see some more questions. Yes.
Yeah. Kotu Shaboda has a question. Please go ahead.
So, hello, am I audible? So thank you, Deepda, for the nice talk. So I had a question, that means when we do usual quantum field theory calculations, we have some initial state and the final state. And we assume those states to be in a flat space-time. Now, when you are talking about dark matter states that's creating standard model particles or dark matter, so means when we are doing in our universe is de Sitter-like. So does the means fact that our universe is nearly de Sitter have any effects on your calculations, or
so our universe is spatially flat, so it's a Friedman-Walker metric where that k is 0. So so even if you include those things, that would be, I think, very negligible effect, because after all, this is locally flat, because these interactions are point like interaction. So it is happening into a particular point in galaxy or whatever. So really curvature, I think, don't matter much in this calculation.
I'm not talking about the interactions. The interactions are locally flat, means that's okay, and the expansion rate is also means greater than the time of the interaction. But means can we proceed by taking the same initial and final states? Because the asymptotic structure is different. That is what I am talking about.
So I really don't know, because I never included that effect, but I think that won't matter much.
Okay, thank you.
So Arsi sir has a question, please, sir.
There is a question in chat box.
Yes, Subhashis Dash, if the universe expands till its density becomes zero, will the dark matter disappear? And as the entropy is increasing, will the dark matter interaction be often? If it happen, what will be the result?
So dark matter do not disappear because the after the freeze out, the dark matter number density is the total dark matter number is constant. So dark matter doesn't disappear.
Okay. So,
Is that answer the question?
Subhashis Das, please unmute if possible.
Either unmute or you can type. I think the commenter says that thank.
Oh, acha.
So then RC sir, please go ahead.
No, thank you. Thank you was already written. But there is also the second question, that if the entropy is increasing, will dark matter interaction happen more often?
So whenever this freeze out thing and dark matter interaction happens, then we assume that universe is isoentropic. So entropy, total entropy is conserved. The entropy density may change, but the total entropy is, it's an adiabatic expansion. So that won't affect my freeze out calculation.
Okay. So, hi Deep. Very nice to hear your voice after a long time. It sounds the same. So I have a question which may be related to what Pratyusha asked, but maybe in slightly different context. Can you go back to where topology is affecting the results or affecting your constraints? Yeah. So freeze out number density of dark matter is higher for higher point interaction. So I was just wondering that whatever you have written about topology, is that the only thing that will, is that the only effect of topology that will happen? Because I thought that there will be other, because you have some theoretical prediction, then you will compare with observation. So I was thinking that maybe there will be other kind of, the universe's curvature, if it's different, then there will be other kind of effect as well.
Okay, so then here all the calculation assuming a particular cosmological model. Here I am doing it for let's say radiation dominated universe. Now, if you calculate these things in an intermediate matter dominated epoch, then this answer would get changed. So of course, these results are specific to the dark matter species. Here I have assumed only one dark matter species and assumed chemical potential to be zero, and assumed this freeze out process happening in the radiation dominated epoch. So with those assumptions, we come up with this number. So if you change alter any of these, then it would be changed. So but the question of curvature, I really don't know. Introducing a curvature effect, I don't think that there will be large changes. So
okay, thank you.
Can I ask a question if there aren't other questions?
Yes,
there is a question from Aritra Kundu.
Okay, there is a question from Aritra, please.
Ma'am, you can go ahead first. Hello, am I audible? Oh, okay. So you mentioned about anti-dark matter. Other than being a theoretical possibility, is there any physical evidence for anti-dark matter? Or can we, if not, can we speculate what sort of difference will it have from normal dark matter?
So all the quantum numbers will be opposite to the particle dark matter, as we know about electron and positron. But we really don't know that there is anti-dark matter or something like that, because it's a prediction from quantum field theory that every particle has has an antiparticle from quantum field theory. But now our universe is only dark matter, there is no anti-dark matter, that we don't know, because we have not found the dark matter itself. We don't know. So it's a possibility just.
Okay.
So ma'am, you can.
Okay. So Deep, when you do, so I think this is two questions, small part. সেটা হচ্ছে তুমি যখন এই ক্যালকুলেশন গুলো করছো, তুমি তো মাস বাউন্ড দিচ্ছ, যে ডার্ক ম্যাটারের পার্টিকেলে মাস বাউন্ড দিচ্ছ, কিন্তু আমরা স্ক্যাটারিং, আমরা ক্রস সেকশন নিয়ে কিছু বলতে পারছি না, বিকজ ক্রস সেকশনের উপর তো কিছু বলা যাচ্ছে না, বলা যাচ্ছে যে সেইং দ্যাট this is a 2-2 process, কিন্তু ক্রস সেকশনের কি কোনো বাউন্ড আছে সিগমার ফর এক্সাম্পল?
হ্যাঁ, আমি তো ওটাই বললাম যে সিগমার বাউন্ডটা তো আমি ওই এস ম্যাট্রিক্স ইউনিটারিটি থেকে দিতে পারি। আচ্ছা, আমি কি দেখাবো? আমি তাহলে এটা কুইট করে আমি তাহলে
আচ্ছা ঠিক আছে, সে দেখা দাও। দ্বিতীয় যে প্রশ্নটা, তুমি তোমার যে ফর্মালিজম ব্যবহার করেছো, এখানে তো আমরা ডার্ক ম্যাটার একটা মানে পার্টিকেল মাস পাচ্ছি, তো তুমি বললে যে মিউ জিরো ধরছো, মানে তাহলে কি এই ট্রিটমেন্টটা কি এসএম পার্টিকেল, মানে এটা কি ফার্মিয়ন, মানে এটা থার্মাল ডার্ক ম্যাটার যে বলছি, কি ফার্মিয়ন না বোসন, মানে এই বোসনিক, এটা তো
বলছি
সেটা যদি একটু বলো।
হ্যাঁ, বলছি। সেটা হচ্ছে যে দেখুন, এখানে এই যে কাই গোস টু স্ট্যান্ডার্ড মডেল, এটা কিন্তু ফার্মিয়নিক বোসনিক দুই হতে পারে। সো মানে আমরা সবথেকে সিম্পলিস্টিক জিনিসটা করছি। সিম্পলিস্টিক হতে পারে স্কেলার, জাস্ট স্কেলার নিলাম। তারপরে যদি আমি বলি আমার একটা কেমিক্যাল পোটেনশিয়াল আছে, তাহলে সেটা আমাকে কমপ্লেক্স স্কেলার দিয়ে করতে হবে, কারণ স্কেলার পার্টিকেলের তো পার্টিকেল অ্যান্টি পার্টিকেলের মধ্যে কোনো ডিফারেন্স হয় না। তো সেই কারণে অ্যাসিমেট্রিকের জন্য আমরা মিনিমাম পসিবিলিটিটা হচ্ছে যে আমাকে কমপ্লেক্স স্কেলার নিতে হবে। কিন্তু ফর দিস প্রসেস, এই যে কাই গোস টু স্ট্যান্ডার্ড মডেল, তার জন্য স্কেলার হলেই হবে। তো এইবার দেখতে হবে, যখন আপনি এবার দেখুন, আমি এখানে ল্যাগ্রাঞ্জিয়ানটা আনিনি, তো এগুলো রিয়েলাইজ করার জন্য প্রথমে আমরা মডেল ইন্ডিপেন্ডেন্টলি এই কথাগুলো বললাম। তারপরে আমরা যেটা করি, একটা টয় মডেল লিখি, যে দেখাই যে এটা একটা রিয়ালিস্টিক মডেলেও হতে পারে। তো সেই পার্টটা এখানে বলিনি। তখন দেখতে হবে যে যদি আমি শুধু স্কেলার বলি, তাহলে এবার স্কেলারের তো মানে স্কেলার থাকলে আমি নানা রকমের টার্ম ল্যাগ্রাঞ্জিয়ানে যোগ করতে পারি, তো সেইটা আবার এই প্রসেসটাকে ডিস্টার্ব করে দেবে কিনা, তো সেইটা আমাকে দেখতে হবে যখন আমি একটা মডেল লিখবো, মানে একটা টয় মডেল লিখবো। কিন্তু এই লেভেলে যদি আমাকে শুধু বোলজম্যান ইকুয়েশন সলভ করে কাই পার্টিকেলের একটা নাম্বার ডেনসিটি বার করতে হয়, তার জন্য এই মুহূর্তে আমার কিছু লাগছে না, মানে সেইটা স্কেলার হলেই যথেষ্ট।
মানে তুমি তো রাইট, ওকে, তার মানে তুমি একটা স্কেলার লাইক ক্যালকুলেশন করেছো, মানে যে স্কেলার পার্টিকেল ধরে ক্যালকুলেশন করেছো, তো সেটা যদি ধরো স্কেলার না হয়, যদি ফার্মিয়ন হয়,
ফার্মিয়ন হলে আপনার স্ট্যাটিস্টিক্সটা আপনি চেঞ্জ করবেন, তখন
তাতে কি কোনো তোমার রেজাল্টে বদল হবে? মানে ধরো কোয়ার্কের মতন হলো, স্কেলার না হয়ে কোয়ার্কের মতন হলো,
সো সেই বদলটা হচ্ছে সামথিং লাইক 10%। আমি যেহেতু ওই স্ট্যাটিস্টিক্সটা চেঞ্জ করছি, এবার যেহেতু এগুলো সমস্তই ডাইলিউট গ্যাস অ্যাজাম্পশন রয়েছে, তো সাধারণত যখন কেউ ফ্রিজ আউট ক্যালকুলেশন করে সব সলভ টলভ করে, তখন ওরা সবাই ম্যাক্সওয়েল বোলজম্যানই ধরে নেয় বেশিরভাগ।
কারণ তুমি কোন স্কেলে, মানে কোন টাইমে ইউনিভার্সের কোন টাইমে ক্যালকুলেট করছো তার উপর, কারণ মানে তার কারণ হচ্ছে যে রিলেটিভিস্টিক, মানে তোমার ফার্মিয়ন এফডি বা বিই নিয়ে ব্যবহার হয় না, বিকজ এটা ভীষণ তাড়াতাড়ি মানে নন রিলেটিভিস্টিক কি বলবো ক্যারেক্টারিস্টিক শো করে, কারণ মাস স্কেলটা আর এনার্জি স্কেলটার উপর ডিপেন্ড করে। যদিও তোমার যা মাস স্কেলের তো একটা ওয়াইড ভ্যারাইটি আছে, মানে জিভি থেকে কেইভি দেখতে, টিভি থেকে কেইভি দেখতে পাচ্ছি আমরা, কাজেই ফলে বিভিন্ন, তার মানে ইউনিভার্সে বিভিন্ন টেম্পারেচার ফেজে তারা নন রিলেটিভিস্টিক হবে, কাজে সেই এফেক্টটা কি ইনক্লুডেড, মানে নাকি তুমি সবসময় ম্যাক্সওয়েল বোলজম্যান ধরেছো?
না, এই ক্যালকুলেশনটা ওই ম্যাক্সওয়েল বোলজম্যান ধরেই করা, আর কিন্তু ওই ডিফারেন্সটা সামথিং অর্ডার অফ 10 to 20%। তো
হ্যাঁ মানে এটা বেসিক্যালি আমরা এমন একটা টাইম স্কেল মানে ধরো ইউনিভার্সে 1 মিনিট পরে বা কিছু, তখন অলরেডি সবই নন রিলেটিভিস্টিক, 100 কেভিও নন রিলেটিভিস্টিক।
হ্যাঁ ঠিক, 1 মিনিট পরে সবই নন রিলেটিভিস্টিক।
সব নন রিলেটিভিস্টিক,
এগুলো সাধারণত নন রিলেটিভিস্টিক ক্যালকুলেশন করেই করে। এবার কিন্তু যদি এটা মানে যদি নিউট্রিনো ডিকাপলিং দেখেন তখন আমার কিছু করার নেই, তখন আমাকে ওই বোসনিক এই সরি ফার্মিওনিক এই এফডি ডিস্ট্রিবিউশন নিয়েই করতে হবে।
সেটা নিউট্রিনোর ক্ষেত্রে, কিন্তু এখানে তুমি বলছো যে তুমি স্কেলার নিয়ে করছো, যদি তুমি ফার্মিওন করো তাহলে 10, 12 বা 10-15% তোমার মাসের বদল হবে। দ্যাটস নট এ বিগ চেঞ্জ ইন দ্য মাস।
হ্যাঁ, আর এনিওয়ে মানে আমরা এখানে তো এখনো মানে ইন্টারঅ্যাকশন স্ট্রেংথ মানে এই আলফাটা হচ্ছে আপনার কাপলিং, এটা নিয়ে কিছু বলিনি, তো সেখানেও আমরা ওটাকে ক্যাপচার করতে পারি।
আচ্ছা হ্যাঁ, প্রত্যুষাব বা আরসি যে কোশ্চেন, ঋতুবান যে কোশ্চেনটা করলেন, মানে আমি জানি না আমি বুঝতে পেরেছি কিনা প্রত্যুষাবর কোশ্চেনটা, কারণ কসমোলজির উপর তো ডিপেন্ডেন্স থাকবে, মানে তুমি এটা স্ট্যান্ডার্ড কসমোলজি নিয়েছো, রেডিয়েশন ডমিনেটেড ইউনিভার্স, এবং ওই আর কি মানে মেন প্রথম কনস্ট্যান্ট আছে বিবিএন। যতক্ষণে তুমি বিবিএন এর আগে থাকছো তখন খুব একটা ডার্ক ম্যাটার মানে ম্যাটার করে, তুমি স্ট্যান্ডার্ড কসমোলজি রেডিয়েশন ডমিনেটেড ইউনিভার্স। ফলে ওই এইচটার মধ্যে যদি নন স্ট্যান্ডার্ড কসমোলজি হয় তাহলে তোমার ওই এইচ এর মধ্যে একটা তফাৎ হবে।
ঠিক ঠিক, যেমন লোকে একটা করে দেখবেন যে ওই ইনফ্লেশনের পরে একটা ইন্টারমিডিয়েট ম্যাটার ডমিনেটেড এপক ধরে, তো এবার ম্যাটার ডমিনেটেড ইউনিভার্স ধরলে আপনার হাবলটা তো চেঞ্জ করে যাবে।
হ্যাঁ, তখন ওই ক্যালকুলেশন। কিন্তু প্রত্যুষাবর কোশ্চেনটা কি ছিল আমি ঠিক বুঝতে পারিনি।
ও যেটা বলছে যে মানে এইখানে আমরা যে এগুলো পড়ছি এখানে আমরা ফ্রিডম্যান ওয়াকার মেট্রিকটা নিয়েছি, তো এবার ও বলছে যদি এখানে কার্ভেচারটা ইনক্লুড করি, কারণ ওই এখন একটা থাকে না ডিআর স্কয়ার 1/1 মাইনাস কেআর স্কয়ার,
না এফআরডব্লিউ তে কার্ভেচার ইনক্লুডেড, তুমি এফআরডব্লিউ এর ফ্ল্যাট কেসটা নিয়েছো।
হ্যাঁ আমি সেটাই বলছি, আমি তো k = 0 তে করছি, আমি শুধু ধরছি যে স্পেশালি ফ্ল্যাট আর এটা শুধু এক্সপান্ড করছে ওই বিকজ অফ দিস a অফ t।
না কিন্তু আমি যে প্রত্যুষাবর স্টেট নিয়ে কিছু একটা বলছিল সেটা আমি বুঝতে পারিনি।
না
প্রত্যুষাবর আছে, প্রত্যুষাবর তুমি একটু বলবে ওটা কোশ্চেনটা কি ছিল আর একটু বোঝাবে?
না হ্যাঁ সে বলুক। ও যেটা বলছিল যে মানে ওই এস ম্যাট্রিক্সে তাহলে ওই এফেক্টটা পড়বে, কারণ আমরা তখন তো কিউএফটিটা তো আমরা কার্ভেচারলেস কিউএফটি করি না, ওখানে তো ওখানে তো মিনকোস্কিয়ান স্পেস নিয়ে করি।
ঠিক, ও আচ্ছা তোমার কি সেইটাই প্রশ্ন ছিল যে তোমার কিউএফটি ফর্মালিজমটা বদলে যাবে যদি তোমায় কার্ভ স্পেস টাইম নিতে হয়, কিন্তু কোনো কারণ নেই কার্ভ নেওয়ার, মানে আমার মনে হয়।
আমি ওটাই বলবার চেষ্টা করলাম, যেহেতু আমি ইন্টারঅ্যাকশন গুলো লোকাল হচ্ছে বা লোকালি এই ইন্টারভ্যাল পয়েন্ট ইন্টারঅ্যাকশনের মতো, তো সেখানে আমার কার্ভেচার এফেক্ট করবে না, সেইটাই বলার চেষ্টা করছিলাম, যে সেটা আমার ধরার বোধহয় দরকার নেই।
ওকে, থ্যাংক ইউ।
আর
so Navonit, so I have no question. There is no question anymore, so we have to stop here. And Navonita, please go ahead for next session.
এই দীপ, থ্যাংক ইউ। আমি একটু জেনারেলি ইন্টারাকশন সেশনটা